Okay, this is my project. I'm going to design a slot machine. And what is a slot machine? You have to match 3 icons or more across different reels. And so that specification has to be hit. So my slot machine is going to be very basic. I know some later slot machines used today have 20 reels, over 20 icons, and to have more than one pay line. A pay line is just straight horizontal match, and I only need one pay line. I know, like I said, some people have 3 and you can have a lot, but 8 icons per reel, and I'm going to use the counter, which will do 0 to 7, and unfair as it is, 0 is a blank, which means you lose, and there'll be 3 reels, and I'm going to name them A, B, and C. You have to pay to play. There's no way around it. So we're going to assume that the person only inputs 1 coin per play. They're not going to keep inputting coins. They're just going to put 1 coin, which in this case will be a penny. And then they're going to be able to play the game. Another thing that this my slot machine will have to do is you could stop all 3 reels in any order you want. I know some slot machines, you just push a button and they stop in order. But this, as basic as this slot machine is, I thought it would be better to give the user more control over the order in which they stop the reels. And then, of course, once all the reels have been stopped, the circuit will then match the icons. So if reel A has icon 1 and B and C also have icon 1, then that's a win state and you win. And the output will be that number. So if it's outputting coins, tickets, whatever, get icon 1 and you match it, you'll get 1 coin, tickets, whatever. So this is just to show you, this is kind of the idea. It's going to have icons, it's going to have 3 reels, and there's just going to have 1 pay line. And it's going to be straight horizontal, and that's it. This is my state table. It's essentially, there's the present states, which are what the user can do to get a win state. The penny must be inserted, and that's going to be 0, no penny, or 1, there's a penny inserted. The reel started. Now, 0, it means the reels have not been started. The player has not allowed them to, not toggled them to start yet. 1, if they have been toggled. Any reel still going. Now, this is going to be considered active low because we only care if the reels have all stopped. And if all these conditions have been hit, that the penny's been inserted, the reels have been started, and then they've all been stopped, will we then have these states. Now, this state table has been greatly reduced because it counts from 0 to 512, all the possible solutions. And you can see we only care about 8 of them, in which it's the matching reels here. And only when they match do we actually care. We don't really care about any of the others. And we can ignore if the player hasn't done the prerequisites, hasn't inserted penny, reel started, and the reels are still going, we simply don't care. And this is the state diagram. It's pretty simple. You start here at idle, no matter what. And then we simply look. Has the player inserted a penny? No, nothing happens. Yes, we will allow the player to toggle the slot machine so that the reels go. And then has this player started the reels? They can choose to just sit there and watch nothing happen, or they could push the button, in which case, if they push the button, the reels will begin to spin. And then this is the point in which the player can stop any 3 reels at any order. So we just look, because we could stop in any order, we just want to know if all of them are stopped. And if they're not, we assume that they keep spinning. If they have stopped, we will look at each count of the reel, of each specific reel. Then we'll ask, do they match? No, you lost, you could start again. And if you win, you'll output a winning icon number, and then it'll go back to the beginning state. Now, if you can forgive me, I'm going to split. I found that the easiest way to do this circuit is to split it into 3 separate circuits. And so, to begin with, we'll do a timing. This will control the slots wheels themselves and count on the icons. To do the wheels, to be able to let the player start and stop the wheels, I found that the bistable 555 was the best choice. In bistable mode, you have a trigger and a reset. Once the trigger is hit, it'll go straight to ground, which will then set the 555 and send out a continuous signal. If you do nothing, this signal will stay high forever. Only once the player has pushed the reset will it immediately send this signal to low and stop the wheel. We will use this with an up counter. This counter will only count to 3 bits. It'll go from 0, 1, 2, 3, 4, 5, 6, 7. We don't care about the last one because we're only going from 0 to 7. So this output is going to be going into the down clock if it's an up counter. The trick here is, if this is high, then the clock is going to be going. Because both of these clocks here, one has to be high while the other is set to a clock. If this is low, then this down clock will be low, and then the whole counter does not work. It does not move. It doesn't count at all. If you notice here, this is also another trick we're going to use to make it so the player doesn't have an advantage. As it is, to save time, all these clocks, because it's going to be 3 of these, mind you, all the clock is going to be the same clock. It's either this wheel A, B, or C are going to use the same clock. And so we can preset the input here so it starts counting from a certain number. By doing that, we set the low all the way to the trigger. So when you set the trigger low, it'll set this number and start counting from there. Therefore, if you set it from 111, it'll start counting. The second you put trigger, it'll begin counting at 111. That's pretty beneficial because if the clock is the same and if they all start at 0, then it doesn't matter where you are. If you stop all 3 wheels at the same time, of course, they're going to be at the same point. So to prevent that problem from occurring, we're going to preset them so that they will, even if you push all 3 wheels and stop them at the same time, they'll never output the same number. Now this is the clock. This is going to be the clock input from here, and it's going to control the up or down counter. Now this is an astable 555, as we learned in the lab that we have done. It's pretty simple to control. The frequency is this equation right here. And so I said we needed a high frequency, so 90 kilohertz should be pretty high so that the user will not be able to just push the button and know exactly when the next trigger is going to be. So solving for that, you find that R1 and R2 have to be 550-ish, but because I use 560 here because it's the most available resistor, so it's close enough to the 90 kilohertz. And C2 didn't change, so we just placed that in here. And C1 for the control doesn't change either, so we just set that there, and that just helps the 555 work. Now, this is the total. As you can see, these are the down count and the up count. To trick the user even more, we're going to have 2 up counts, which means 2 of the wheels will be going up. So it would be going from 0, 1, 2, 3, 4, 5, 6, 7. One of them will be counting down. So 7s and 6, 5, 4, 3, 2, 1. All of them will have the same clock source, this one astable 555. Now, we have the input output here. That's going to have each specific wheel. There's going to be 3 of these. Now, we have 3 bits, there's 9 bits in total. And we're going to name that each one here. So this is going to be just comparing 2 of the wheels, A wheel and B wheel. Now, this is going to be, to simplify it, we're going to use the principle A equals B equals C. If we can prove that wheel A is equal to wheel B and wheel B is equal to wheel C, we could ignore having to compare wheel A with wheel C. And this will save space in the long run. But for now, we're going to have this, and this is the monstrosity that we get on the output of this Karnaugh map. Now, we don't want to deal with this. This is not good design for the PAL or the MUX that will be used later. Oh, sorry, the gate and the MUX. This will be used for the PAL. So this is going to be, we're just going to compare two of the highest bits, because we don't want this long on Karnaugh map app. We realize, why are we doing this long thing? We could just compare the two highest bits, and we realize it's a NOR gate. We're just using a NOR gate. And so I'll now go to MUXes, and then gates, then PL. But for MUXes, we realize that because it's just a NOR gate for the two highest bits, we could then do it like so, and this will compare the highest bits and whether they match. Now, we still have two other bits, and that will be A2, A1, and B2, B1. And we can then simplify this into an 8-to-1 MUX. Now for this, we can prove this A equals B equals C idea. Now, here would be A3, B3 will be the highest bits. And then it'll go and do A2, A1, B2, B1. And of course, we're trying to prove that A equals B equals C. Otherwise, we would have to use another set of MUXes to be able to prove that A equals C. So what we're going to do is that we're going to take that condition we talked about earlier. We're going to take only when the wheels have stopped. We only care when they stop, so it's going to be 0. Remember that the MUX has an active low input, or enable. So only when it's 0, we're going to look, and then this is going to activate only once all the wheels have stopped. So basically, the matching circuit will only happen once the wheels have stopped. So this will activate. Then we're going to take this one and cascade it to the next one. So that means the A3, the most significant bits, must match for the next bits to be checked. They must match that match. If these match, that means A equals B. If A equals B, then we can move and check to see if B equals C. Of course, if all this checks out, it'll output a RIN. And if it outputs a RIN condition, then we know A equals B equals C, all the wheels match. Now, this idea is the same for gates. We have the only difference is that because the MUXes use an active low enable, we're going to use a NOR. Again, to get a 1 output only if all the wheels have stopped. And again, we can use the same idea before of cascading, but this time we use the exclusive NORs to check only if these bits match. So we first check A3, B3, that matches. Then B2, A2, and then A1, B1. If that matches, we know that A equals B. Then we go on to B3 and C3 and so forth. Only then will we get a ring condition on the output and know that A equals B equals C, and all the wheels match. Okay, so the Karnaugh map solution we found here will be used for the PLA here. Now, we can't necessarily do cascading on a PAL. So to prove that A equals B equals C and saves the programming space, we're going to connect an AND gate to the outputs here. That means we only have to program for A equals B and compare all the A bits to the B bits and compare the B bits to the C bits. And if we AND it here, we'll prove that these two are equal to each other. And therefore, once again, A equals B equals C. Otherwise, we would have to take A here, compare it with C, and have another 8 AND gates and another output. And we would still need an AND to these outputs here. Now, we've successfully done most of the state table. The only thing we haven't looked at yet was coin input and output. And this can be put into its own circuit here. What we're going to do is use flip-flops. One for the output, in which you've already won, and one for the input to make sure the player has inputted a coin. Now, this is a little weird, so I'm going to try to show it. The condition is basically like this. we know that once this is going to be the equivalent of this NOR gate here, in which the wheels have been stopped. You're going to input the coin here. The player is going to start the wheels. This is going to be high. Now, this is outputting a 1. This means that the coin is out there and it's going to power the rest of the circuit. Now, the second this goes low, and then it'll be stopped and restarts, it'll go low. And this resets it. This means that the player would have to put another coin back in to play. Now, as you can see, as I said, this coin is going to become the power for the bistable 555s. That means it'll only, these bistable 555s and you being able to trigger them or stop them will only happen if a coin's been inputted. But also, it's going to go and reset it. That means this reset is only to clear these flip-flops from the output after every win and once you put in another coin. So it doesn't output the wrong number or icon after. It's just going to go straight to 0, 0, 0. And 0, 0, 0 is a blank. It means nothing. It's you lost. And the ring condition is going to be the clock here. By connecting the ring condition to the clock, it's going to be 0 until a match. Once it hits a match, it's going to go 1 and load these bits in. It doesn't matter if it's A bits or the B bits or the C bits, because we know the same, A equals B equals C. Doesn't matter, it's going to output this for the player, and this is going to be the form of coins, tickets, whatever. Now, I'm going to compare all the circuits. Now, the timing circuit and the coin output circuit are integral to the actual design. We can't get rid of it. So this is going to be used no matter we use muxes, pals, or gates for the matching. And only the matching, it has 3 different actual circuits. The timing circuit and the coin output circuit are the same, aimed throughout. So I use these because I used 4 555 timers, and 3 in bistable, 1 in astable mode. I'm going to just use a 556 to save space. I'm going to use these flip-flops here. I have to use 5. It's going to be $4.27 no matter what. Of course, all these prices are for 1 unit, and if you mass produced it, it'll drop a lot. You could divide by 2 and get the actual mass produced for about 1,000 units. For the mux, we're not really lucky here, because unfortunately, this uses a NOR gate. A NOT gate for the mux, and the NOT gate has a power requirement that's different than the rest of the circuit. The whole circuit so far has been using about 5 to 5.5 volts. The NOT gate will be forced to use a 5 volts, so this might, you have to be careful about the power concerns here, and this is only applicable to the mux. The PAL is probably the best, it's the cheapest. It uses less space, and the gates uses about the same number of ICs as the mux, but also cost a lot. So the final circuit here, as you can compare all the pricing, the mux is going to be the most expensive, but it uses the same amount as the gate. If you can get lucky and the PAL you can get it for a low enough price, then it would be better than using, say, any of these. Now remember, the timing and coin are in all of these, because without the timing, you will not be able to start or stop the wheels. And without the coin, you will not be able to see whether a player has inputted the coin. So this is important and will be in all these. But based on pricing and size, I will say that the PAL is the best for this circuit. That is because not only will be using less gate or less ICs than, say, the gate or the muxes, it's considerably cheaper and will use less powers than the gates, which has to, each individual IC for the gate will have to be be powered, and because the mux also use some basic logic like the NOT gates and a NOR gate would also have to be individually powered. And that's it.
Thank you very much. Any questions at all from anybody? I have 2 or 3 questions, but before, yeah.
No, this is actually done differently than a real slot machine per se, because those use a real number generator. They have a long list of tables, and like you said, each in that table they make it so the chances are different. So the ring jackpot will have only like a one specific number it can happen, but the lowest number that can happen would be like a million different numbers. This one, all 512 numbers in the state machine have a fair chance of happening. They're all equal chances.
Great. Any more questions? Right. Andrew, this is again one of those fantastic design. So let me just ask my questions before we go any further. The only concern, it seemed to me, I could be wrong though. I mean, now that I'm looking at this design, I'm just wondering whether this system will work synchronously with your clocks. Let me tell you why. You know, in order to compare A to B to C, you obviously need a really fast clocking system then, because you don't want this comparing to take time, correct?
Okay.
And yet, when we go to your state diagram, if we go back to your state diagram, right down here. So down at the bottom of third state down, that where they call the spin reels.
Okay.
When the spin reel went, the condition said no, you went back to the same state without allowing a second consideration for that clocking system. You know, when we were designing the bus Arbeiter,
Okay.
how we went taking care of this timing system twice. You did not take that consideration, assuming the timing would cope with this. So for these 2 reasons, one, you compare A to B to C with clocking one to the clocking next and clocking next and clocking next.
The clocking actually only occurs for the counter when the wheels are spinning. Once the wheels have stopped, the counter will not be able to count anymore. The clock may still be going, but because the way you input the bistable to the counter, it will immediately stop, which means it'll only output the last known count, which will go straight into the matching circuit.
Absolutely. This is right. This is how I understood it. So the clocking for that would be fast, right?
It should be very, yes. Because
Right.
it'll meet the immediate once the wheels have stopped, because I added this little gate. Let me see. When I cascaded it, I added this. This circuit is only activated once the wheels have stopped, and by extension, the counter will have stopped at a specific number. Then the inputs will immediately go into here, and they'll start going based on the logic.
Right.
So it should be close to instantaneous.
Right. So you're using 3 clocks, in fact.
No, one. The A stable is connected to the counters. It shows 3, but I'm just showing that in a case where it's a down count and an up count. But this one astable 555 will be used as the clock for all counters to save space.
Yeah, I understand using, but you have 3 clock output, do you know?
I don't understand.
What I'm not sure, it could be that I'm too slow to understand that how come clocking somewhere requires to be slow and other places it needs to be fast. I don't get that.
I mean,
for the wheel, it seems to me, because it's a mechanical move, right?
it'd be, well, in this case, it's all digital because it's all in
Okay.
circuits. But
Right. Yeah. Okay. Even digital, but actually, because you need to see it visibly, you need something to real for you to see. So you need time. You need seconds of time. If I'm right.
For this case, it would be going so fast you wouldn't be able to see it. I mean, a lot of the reels that are used today digitally, they just spin it all, and based on that, that's outcome from the random generator, they show it. But if you ever looked, the way they spin is considered instantaneous, and then just stop on a predetermined output. So you wouldn't know you couldn't time it per se, because it's spinning so fast. So you wouldn't be able to know what the outcome is until you stop them.
I see. Well, that shows I'm not a good gambler. Okay. I've never been to any slot machine room, to be honest. I just, I went, I don't know, Las Vegas, and I saw 1 or 2 just by walking by. Okay, so I have to, I mean, unless I sit down and look at this report, get more, I mean, more, precisely, I won't be able, but I take your word for it now. I think you're actually right. I mean, but let me also say that your design is just absolutely fantastic, so clever. You know how you went about tackling different problems so cleverly and innovatively, how you compared numbers, how you went about taking use of resetting and taking care of the count. I was absolutely amazed. I mean, how beautifully you did this. So it was a very, very clever design. Not only design work, it's intelligent. It really is clever. I really liked it. Again, I think this is presentable too. I mean, to other manufacturers, and you also presented very well, Andrew. I enjoyed listening to everything you said. I had your diagram was very, very clear. Everything was beautifully done. You too are exempt from the final exam. Thank you very much. I'm really, really thankful to you.
Thank you.